So good evening, one and all. I welcome you to the eighth live session of the NPTEL course, Soil Hydraulics and Pneumatics. The tutor for this particular course is Professor Somshakara Siramat from the Department of Mechanical Engineering, IIT Madras, and I am the teaching assistant for this particular course. I hope you have gone through the lecture videos and have attempted the assignments for the previous weeks. If you are having any problem, we can discuss in this session after discussing the um, questions. Okay, so coming to the first question, it's a numerical. So a hydraulic motor is having a volumetric displacement of 163 centimeter cube. It receives 0.0008 meter cube per second of oil at 60 bar pressure. Find the theoretical torque and theoretical power in kilowatts for the motor. So it's the direct question from the assignment. I hope you have tried. So let's of motor. It's 163 centimeter cube, and Q has been given as 0.0008 meter cube per second, and delta P, which is the pressure differential across which the motor is operating. It's 60 bar. So your first work would be to convert this into SI units. I am not writing it here, but while doing the calculation, I will wait. So you're asked to calculate the theoretical torque and the theoretical power of the motor. If you are knowing the formula, then it's fine. You can directly plug into it. But in case you are not able to recall the formula, then there's one thumb rule. So basically, for hydraulic motor, what you have, suppose this is your motor, this is the particular fluid power symbol for motor. So what you are seeing, there is some hydraulic fluid which is coming into the motor and it is running across a delta P. So the fluid that is coming in is coming at a particular flow rate, and it is a pressurized fluid. So in case of and yes, the shaft of the motor is rotating. Now the fluid that is coming into the motor, this is the actual flow rate. Okay. Now a small amount of this will be lost in the form of leakage. Okay. So the remaining amount of fluid is what your theoretical flow rate that is consumed by the motor. So what you can write here is Q theoretical is your Q actual, that is the amount of liquid that is ideally flowing into the system minus the loss that is happening. That is the leakage loss, and also some compressibility losses. So you can understand that Q theoretical is obviously less than your Q actual, right? Now, if you look at the output, so here what efficiency comes into picture? It's the volumetric efficiency. Your volumetric efficiency is nothing but your Q theoretical, which is the smaller quantity, divided by the Q actual that is actually coming into the motor. Whereas if you look at the output side, so you have the theoretical torque that is produced by the motor, that is supposed to be produced by the motor. And how is this produced? By conversion of this theoretical fluid energy into the mechanical energy. Okay. So the fluid energy corresponding to this particular flow and pressure. So basically your Q theoretical multiplied by delta P is completely getting converted into 2 pi n theoretical. So here we are not considering any loss because this is the conversion, like there is no conversion loss. We are assuming, but during the transmission there are some losses. So that is the mechanical loss due to friction and all and inertial effects. So you have some efficiency associated with that. So that is nothing but the mechanical efficiency. And what you're getting as the final output is your torque actual. If you are able to remember this entire picture, then it will be like very convenient to solve these any of these numericals. So you will be given with some of the parameters, uh, and you will be asked to calculate accordingly. This is your fluid energy, and this is your mechanical energy. So here I am considering no conversion losses. But as I showed here, there are some mechanical losses. So your mechanical efficiency will be nothing but what is the smaller term here? It is the actual torque divided by theoretical torque. Okay. So anyway, this much was not required in this question because it is directly asking you about like there are no loss terms which is being asked here. So you can directly use the data in the question. However, this will be required in the next numerical. Next question, that's upcoming question. So I'm just keeping it intact. Or what I can do is just I can cut. Yeah, this question will be requiring because where did it go? Okay, yes. Let it be here. I will be coming here after solving this question. Okay. So here it is asked a hydraulic motor has a volumetric displacement of this one. Okay. So once you're given with the volumetric displacement, you will be expecting that there should be some rotational speed of the motor. So if you multiply your rotational speed with that, you will be getting your discharge. Okay. So what you can write is your Q is equal to VD into N. Okay, so N hasn't been given in the question, and you don't require that also because you're asked the theoretical torque. So what you will do, you will equate the input and the output power. So power input to the motor is equal to the power output from the motor. So what is your input power? That is the hydraulic energy carried by the liquid, uh, the hydraulic liquid. Here you're not given any efficiency value, so you can directly equate these two terms. So the hydraulic power is nothing but delta P multiplied by Q, and that is equal to the output power, that is the rotational the rotational kinetic energy and the power associated with it. So you can write it as 2 pi n into T. Okay, so from here, instead of Q, you can, yeah, so you know that Q is equal to VD into N. So you can write delta P multiplied by VD multiplied by N is equal to 2 pi N multiplied by T. So N will get cancelled and you will be left out with T, which is equal to delta P into VD by 2 pi. So this is a direct formula. You can remember this also, or you can just apply this simple conversion and get the formula. So you're given with delta P, it's 60 bar. You have to convert it into Pascal. So into 10 to the power 5 multiplied by volumetric displacement is 163 centimeter cube. Again, have to convert into meter cube. So 163 to 10 to the power minus 6 meter cube divided by 2 pi. Excuse me. You can also calculate along with me. So directly you can see here in this 0 and 10 to the power 5 will It cancel out with this. So 163 multiplied by 6 by 2 pi. So what you will get is 155.65. What will be the unit of torque? It is Newton meter. So this is the torque that your motor is producing. So the output of the motor. Now the next question is, what is the theoretical power of the motor? So as we know that here you are not given with any efficiency, so you can directly write theoretical power as your 2 pi n t. Okay, so again you don't know n, so can either try to find out n from this equation, or you can directly use the theoretical power as delta P into Q, since there are no losses here. Had there been any loss, then your theoretical power should have been 2 pi n into T theoretical, or your delta P into Q theoretical. So here Q theoretical is being considered as same as Q actual. So no need to worry about that. 60 into, sorry, so 60 multiplied by 10 to the power 5, and Q is 0.0008 meter cube per second. So we will be getting how much? So 60 to 0.0008. So 4.8 kilowatt. Now you just check the options. 155.73 Newton meters, so that is close to 155.65, and 48.01 kilowatt. So there is some mistake, or else the answer is coming as 4.8 kilowatt. So if you are able to see the question carefully, and if you are having some estimation capability, then you can understand that this value of Q, this is not correct. I mean, your pump, sorry, the motor, your flow rate through the motor can't be this less. It should be more, because another way to find out is by using this. So just calculate the value of N. So your N should be 0.0008 divided by VD, which is 163 into 10 to the power minus 6. Okay, so that will be revolution per second. If you divide by 60, then you will get revolution per minute. So you try to calculate this. 0.0008 divided by 163 by 60 into 10 power 6. Oh, sorry. It should be multiplied by 60. Revolution per second. So if you convert to minute, then it will be multiplied by 60. You will get around 295 RPM. So if you see, this is very less value. Generally, your motor speeds will be in thousands, like some 2000, so like 10 times more than this, around 3000 RPM. If you just see the next numerical, you can see here the motor speed is 2000 RPM. So you can understand that 295 RPM or 300 RPM, it is not the correct, not a correct value, like under steady operation conditions. So ideally, what I feel is the 10 should be less here. Okay, so This question is there in your assignment, so you can just so this power range is correct, but what we got, this is less. Okay, like under, again I'm saying it is under steady running conditions. Okay, so as soon as we will reduce this, we'll get 48.01 or 48 kilowatt. So then this option would be correct. Let's see. So you could ask whether this torque will also change or not. But you should keep in mind that torque is not dependent on Q. Torque, you can see here as we are equating this, torque is not dependent on the flow rate. Torque is dependent on the pressure at which the fluid, at which the across which the motor is being operating. So, and VD is anyway constant because that is the design characteristics of the motor. So T will not change. It is independent of Q. So we got three, four uh, insights from this particular problem. It is a simple problem. So, but still, like a few things we got to know. Next question. A hydraulic motor has a volumetric efficiency of 94%. So I'm just writing it down. Um, yeah. Okay. So a hydraulic motor is operating at a volumetric efficiency of 94%, and it operates at a speed of 2000 rpm and a pressure of 85 bar. If the actual flow rate consumed by the motor is 0.0068, you can again see that here it is a correct value because it is like there you have one more zero after the decimal. So here in 0.0068, so it is a plausible value. So Q actual is given as 0.0068 meter cube per second, and the actual torque delivered by the motor is 162 Newton meter. So torque actual is 162 Newton meter. Find the overall efficiency of the motor. Now, if you are pretty much acquainted with this entire picture, particular thing, then it is just a single line problem. Like you will just need to equate the input and the, sorry, you just need to find out the actual output power and the input power to the motor. Okay, then the overall efficiency is nothing but the output divided by the input. But if you just break down it into multiple steps and then try to solve, so I would just like to add two more things here. So this is the fluid energy that is being taken up by the motor from the actual energy that is getting as the input, and from here the actual output is nothing but 2 pi n into torque actual. So here you have the fluid based losses. So your volumetric efficiency comes into picture here. Here the mechanical efficiency comes into picture. And if you know that if you multiply these two efficiencies, then you will get the overall efficiency of the motor. Correct. So I will try to solve it both ways. So first, I will just do it at, using the single step thing, as I said. So what is your output power here? As I said, it is the output that is coming out finally. That is nothing but 2 pi n into actual value of the torque. Okay. So if you try to, so what I will do, I will substitute the values finally in the overall efficiency formula. And what is the input to the motor? The actual input. So that is nothing but delta P into Q actual. That is the fluid energy, and this is the mechanical energy. This is the fluid energy, this is the mechanical energy. Now your overall volumetric efficiency is power output from the motor divided by power input to the motor. And you are given with this actual value of torque and Q. So 2 pi into n is 2000 revolution per minute. To convert into SI, you have to convert to seconds. Or, yeah, okay, multiplied by torque actual, that is 162. It is given in Newton meter, so that's SI only. Delta P, 85 bar, multiplied by 10 to the power 5 pascals, into Q actual is 0.0068. Again, it is given in SI. Just try to substitute the values. Sorry, try to calculate this. Get 2 pi multiplied by 2000 divided by 60 multiplied by 162 divided by 85 10 power 5 6 8. So I'm getting around 58.7. So this will give me 0.587, which is also written as 58.7 percentage. Okay, so this is the direct thing. If you are acquainted with this entire picture, then it is easy to get this. However, if you want to solve it step by step, then also it's possible. Just it will be a little more meticulous. So first you have to calculate. So this is your one way. Second way is you have to calculate step by step. So your volumetric efficiency you are knowing. You have to calculate the mechanical efficiency. So your mechanical efficiency is actual torque divided by theoretical torque. How we will calculate the theoretical torque? By equating the fluid energy and the mechanical energy, that is the theoretical values of both. So delta P into Q theoretical is equal to 2 pi n into T theoretical. And how will you get Q theoretical? Again, you're given with the volumetric efficiency, so that is Q theoretical by Q actual. So your Q theoretical is eta vol divided by multiplied by Q actual. So your delta P is nothing but 85 into 10 to the power 5. Q theoretical is eta volumetric, that is 0.94 multiplied by actual is 0.0068 is equal to 2 pi into n is 2000 again divided by 60, you shouldn't forget, into T theoretical. So from here you will get T theoretical just try to calculate this. 5 multiplied by 10 power 5. So you'll get around 259.42, around 260 Newton meter. Okay. So from here you will get your mechanical efficiency as T actual, which is given as 162 divided by 259.42. So I'm getting it around 0.624. Now all you have to do is, sorry, I just did a mistake here. It's not volumetric, it's overall efficiency. That's what asked in the question. Volumetric multiplied by the mechanical. So one is given, that is 0.94, and the other is 0.624. You'll again get around 0.587. So this is the longer, little bit more elaborate procedure. You can follow either of them. Either ways, you're getting the same answer because it boils down to the same formula. So what is the main takeaway from here? This particular thing. So once you're thorough with this entire picture for a motor, it will be easy for you. Now, same thing if you try to just deviating from this topic a little bit. If you try to do this for a pump, then how will it look like? Before solving the next question, I'm just trying to draw this thing, this particular picture for a pump. This particular thing for a pump. So you have the sorry. Right. So it is again operating against a pressure delta P, pressure differential again. Then here, if you see that you are giving the energy into the pump. So not you, I mean, there is a motor that will be giving the energy to the pump. Motor or some engine that will be giving the energy to the pump. So this is your input. So here it is rotating, say at a speed, at a torque of T theoretical. It is facing some mechanical inefficiencies due to frictional losses at the bearings or uh, due to inertial factors. Then here you have the actual torque, which is helping um, the pump to draw fluid from the low pressure end to the high pressure end. So this is the pressure differential, as I said. Now, if you look at the volumetric flow, so it is trying to you know it is trying to draw a theoretical flow rate of qth. But what is happening? There are some losses happening. The losses, it can be leakage loss or due to compressibility. There are some compressibility of the hydraulic fluid. There is some loss of energy. So what is being delivered by the pump? It is Q actual. Okay. So this is your output. This was your input. Now, if you try to look into the energy terms, then it will be easy. So here, your volumetric efficiency comes into action. So your volumetric efficiency is nothing but here, which is the smaller term, your Q actual is the smaller term because that is the output here divided by Q theoretical. Okay. So here, you need to keep in mind that Q actual is Q theoretical minus the leakage. So I'm considering leakage only, but there are some other losses due to compressibility. Here it was the other way around. Q theoretical is equal to Q actual minus QL. Here Q actual is Q theoretical minus QL for a pump. That was for motor. So obviously your volumetric efficiency will be Q actual by Q theoretical, and your mechanical efficiency will be actual torque divided by the theoretical torque. Okay, so the energy conversion equation from mechanical energy to fluid energy. So what is your what is your input? Input is 2 pi N into T theoretical, but it is not getting completely not going to the pump. So there are some losses due to friction. So you're getting 2 pi N into T actual. This is the mechanical loss. Now this is converting. So this is the mechanical energy converting to fluid energy. That is delta P into Q theoretical. Okay. This is the fluid energy. I'm considering that in this particular conversion there is no loss. Then again, when what you're getting is actually the output, that is delta P into Q actual. So these two are the fluid energies, this term and this term. So in between this, you have the leakage and compressibility losses. So in between this, your mechanical efficiency will get plugged in. In between this, your volumetric efficiency will get plugged in. And as you multiply both, you will get the overall efficiency. This is the only you know difference between the motor and pump. Otherwise, like for solving numericals, both can be approached in a similar way. Okay, so this was not a part of this particular numerical or even the agenda for today's discussion, but I just took this up since we discussed for a motor. The same thing could have been discussed for from the point of view of pump. Okay, coming to the next question, and the numerical. A single vane oscillatory type rotary actuator has 14 mm outer radius of the rotor, 40 mm outer radius of the vane, 20 mm width of the vane. If the torque load is 120 Newton meter, what must be the pressure in megapascals? You have to be careful about the units asked. developed to overcome the load? So it is again straightforward question. So you have a single vane oscillatory type actuator or motor. Let's say this is the vane at the extreme position, and this is your rotor. You have inlet and outlet. Now we are given with outer radius of the rotor. It is 14 mm. Outer radius of the vane is 40 mm. And your width of the vane is 20 mm. So what will be the so once you're these are the geometrical features of the particular motor. So from here you can get the volumetric displacement VD. Since you've been asked to calculate the pressure, so your Q, that is the flow rate, is 2 pi n into T. N is not given, so you can write delta P into VD multiplied by N, that is also Q, multiplied by 2 pi n T. The N will get cancelled. From here, you need to calculate delta P, which is 2 pi into T, or you're given the torque load divided by VD. VD you have to calculate from here, from the given data. So the annular space is nothing but PR vane square. Again, this is not diameter, so I'm not dividing it by 4, minus R rotor square multiplied by W vane. I into 40 square minus 14 square multiplied by 20 millimeter cube. How much will you get? 40 square minus 14 square multiplied by 20. So I'm getting 88.22 centimeter cube because I am dividing by 1000. So better to convert it into meter cube, but it's fine. Like okay, you can also convert it in meter cube. So it is nothing but 1, 2, 3, 4. So I'm getting 0.0882 meter cube. So we are plugging the values here. 120 Newton meter divided by 0.0882. So what I am getting is 8547 Pascal. So in question it is asked in megapascal. So 8.55 megapascal is the nearest answer. It's pretty straightforward question. Again, this question can be uh, tweaked around by putting in some efficiency terms in terms of volumetric efficiency or mechanical efficiency. All you have to keep in mind is this particular thing that we discussed. So this should be the thumb rule. Now, okay, let's get into some theoretical questions. What are the functions of which of the following are the functions of hydraulic reservoir? So I hope that you have gone through the videos, you have understood what is the role of hydraulic reservoir. It's not just a storage tank for the hydraulic fluid. It has multiple other functions also. So primary function is storing the hydraulic fluid, obviously. It promotes no heat dissipation, that is wrong. It promotes heat dissipation. It allows no entrant air to escape. It is it is wrong. It allows the entrant air to escape. Rather, it it can be used to separate the contaminants by using baffles and all, and strainers. Are the correct answer. The following points hold good for Newtonian fluid. Again, it's basic fluid mechanics question. Possesses viscosity, no viscosity. Shear stress is directly proportional to the rate of shear strain. Shear stress is not directly proportional to the rate of shear strain. Shear stress is more than the yield value, but proportional to the rate of shear strain. So, the answer is quite obvious. It possesses viscosity, and shear stress is directly proportional to the rate of shear strain. Just for some supplementary information, suppose you try to plot the graph between the shear stress and the velocity gradient that comes upon application of the shear stress. So for ideal fluid, which is having ideal fluid means it can flow without the effect of any friction between the layers of fluid. So that means there is no viscosity. Viscosity is basically due to a type of fluid friction. It acts between two layers of flowing fluid molecules that doesn't that generally restricts or tries to slow down the relative motion. So this is we have come across this in fluid mechanics course already. So this is the line for ideal fluid, because ideally you don't require any shear stress to allow the fluid to flow, because it's ideal fluid. It doesn't have any friction, so you don't need an external aid to overcome that friction. If you talk about ideal solid, then it is having zero capability to flow. Okay, so how much shear stress you apply, your du by dy will be zero. So this is the line for ideal solid. Now, if you look at Newtonian fluid, Newtonian fluid is it is a category of fluids wherein the value of shear stress is directly proportional to shear strain, and the proportionality factor is nothing but dynamic viscosity of the fluid. So this is the constant. So this is your Newtonian fluid. So what is non-Newtonian fluid? Any fluid that is not following this particular equation is your non-Newtonian fluid. So it can have different representations. Can be like this or like this, depending on the behavior of the fluid. There is another category of fluid. So these are non-Newtonian. There's another category where you need to give an initial, you need to overcome an initial value of the shear stress to allow the flow of the fluid. So once you overcome that initial value, it again flows like a Newtonian fluid. So we call it Bingham plastic. Bingham plastic. I hope you have come across this term in again fluid mechanics. So that is also known as ideal plastic fluid like that. So, what is this particular value of tau s? That is the yield value. So this is the particular option for Bingham plastic. An example can be the toothpaste that we are using. So you need to apply a certain level of stress to allow the flow to be happening from the to extrude it from the tube. So that can be one practical example. Okay, so okay, coming to continuous generation of heat. So the temperature goes on increasing. It can cause some adverse effects to the hydraulic fluid or even the um, subsystems or the components, like undesirable expansion of the component seals and all. Then, uh, you know, there can be changes in the viscosity of the hydraulic fluid at higher temperatures. The hydraulic fluid may get very thinned out. It loses its viscosity. Then it won't be able to, like there are chances of loss. QL will increase, and also like it will not be able to carry the energy substantially. So the delta P value may be less, because what is delta P? It is basically the resistance. It is coming due to the resistance of flow. If there is no resistance, that is, it is not viscous enough, then your delta P will be less, and the energy will automatically come down. So you need to take care of the main points at which this heat generation can occur. So one of it is your pump. Continuously you're supplying energy to the pump through a external electric motor or an engine, IC engine. So there, due to frictional losses, the heat energy is getting dissipated. Your pump may get heated up after some considerable amount of considerable duration of operation. Then your pressure relief valve. So in your PRV, what happens that it opens opens against a particular um, fluid pressure. So indirectly, it means that it withholds or withstands a certain threshold value of fluid pressure. So If you look at PRV, say pressure relief valve, it is a general representation, heat power representation. So this is your system pressure. It leads the system pressure, and it has a spring. So that spring it keeps the particular line generally closed, normally closed. So NC, I'm saying, say. So if this particular pressure it exceeds the threshold value, which is determined by the which is again set by the variable spring, variable stiffness spring, then this opens. This particular valve opens, and it releases the energy. But before, like if it's up, if the pressure is some like there is some finite value of pressure which is less than PTH. Okay, so then also like there is some amount of uh, you know energy that is being resisted. The energy means the flow fluid energy that is being resisted by this particular valve. So obviously there will be chances of heating up. This energy needs to be converted, right? That this particular energy, which is not the fluid energy, which is a pressurized fluid, it tries to flow but it is not able to flow. So part of it will try to will try for leakage. If there is some leakage path, then it will try to flow out of that if it heated up. So inside the PRV also there is possible generation of heat, heat dissipation. Tank generally, tank in the tank heat is not generated, rather it is dissipated, because there is no source of energy that or there is some restriction to flow that may cause the generation of heat. In your flow control valve as well as direction control valve, there are some channels that either restricts the flow or it deviates the flow. So there, due to changes in momentum that comes from the changes in fluid velocity, there will be some losses. So that loss is getting dissipated in the form of heat. So there also possible chances of heat generation is there. So FCV and DCV will also be considered. How to overcome seal failures? So in hydraulic systems, many places seals are used, particularly where you have mating parts and you don't want the pressurized fluid from one side to leak into the low pressure region on the other side. For example, in a double acting piston or single acting also, like in such cylinders, you don't want the pressurized fluid to um, you know leak to the other side, that is the low pressure side of the piston. So there you need seals. So how obviously for a particular hydraulic system, once you have chosen the seals, you need to like once you're choosing the seals, you need to take a few things into consideration. So let's go to the first option, by adjusting the flow rate. I'm coming to this later. By a proper seal geometry design, yes, you have to select the proper geometry. Geometrical aspects means the diameter or the thickness of the thing, of the seal, or the length of the or the width of the seal. So these are the geometrical designs, the clearance and all those things. By proper seal material selection, yes. So what type of fluid core application is there? Like what is the fluid against which you're providing the sealing fluid flow? Like if it is a if the hydraulic fluid is it can be corrosive, it can be operating at a higher temperature or pressure. So whether this particular seal material is able to resist that, whether it is able to sustain that, that comes into picture. So your proper seal material selection is important. Next, by proper seal installation, it needs to be installed properly, so that the clearances and all are optimally maintained, and it sits properly in the piston. So generally, if you are having cylinder like this, there is the piston. So here you have you give the seals, O-rings generally. So two grooves are cut on this particular piston around, these are peripheral grooves. So in between the grooves, the O-rings are installed. So this installation is also important. Now coming to the other two options, adjusting the flow rate, adjusting the system pressure. These two doesn't allow us to overcome the seal failures. We shouldn't, you know, adjust system pressure and flow rate just to protect the seal. Rather, the seal should be selected by taking into account the Q and the delta P. So these are the input things while input parameters while designing a particular seal or while selecting a particular seal material. So these two shouldn't be adjusted. Okay, so you should keep in mind these two affect the seal failure. That is correct, but they are not changed to overcome the seal failure. Steel tubing has a 20 outside diameter, 50 inside diameter. It is made up of soft, cold drawn steel having a tensile strength of 3200 bar. What would be the safe working pressure for this tube, assuming a factor of safety 9? So as you can understand from the question, this is an application of hydraulic conduits that allows the flow of the hydraulic fluid from between different components. So, like there are different modes of, you know, there are different, considerations that should be taken care of while selecting a particular uh, this thing tubing. So number one is your frictional frictional losses that can be happening inside the tubing. So accordingly, you should be optimizing the length and diameter of the tube. Then your ability of the particular tube to sustain the fluid pressure. That is one of the most important considerations, because uh, accidents in these hydraulic systems can cause potential hazards not only to the system or but also to the workforce who is working around the machines. So these two are the main considerations. Then leakage is another thing. So this question it pertains to the pressure rating for a particular steel tube. So your outer diameter is 20 inner diameter is 15 So the material you're given. So these are the geometrical things. Geometrical. So what is the thickness then? 20 minus 15 divided by 2, right? 2.5 So if this were radius, then you shouldn't be dividing this. So you're given with the tensile strength 3200 bar. So in multiplied by 10 to the power 5 Pascal. Now you have a direct formula to calculate the pressure at which this can, you know, this can lead to failure. So generally, it is being derived by uh, considering a thin tube. So for a thin tube, suppose P is the working pressure, outside diameter of the pipe divided by 2 into T. PD by 2T is equal to your tensile strength. So if this is your, so what is this pressure? So if you're equating this with your tensile strength, it means that you're working at the extreme condition, right? If this particular pressure is uh, it is producing this much amount of um, tensile stress in the tube, then it will lead to failure because it is having a tensile strength of this much. So what you have to do, you have to maintain a particular factor of safety. So to calculate the working pressure, what you will do, so to calculate the working pressure, you have to divide it by the factor of safety. Okay. Now PWP is 3200 into 10 power 5 divided by factor of safety. You can see what is the factor. Since so this is the steady state pressure that we are talking about. So there can be some intermediate hikes in pressure due to your some shock waves that is generated within the fluid circuit. So that again comes into picture when there is suddenly some blockage in the flow. Suppose when the valve is closing or it is shifting from one path to another, then there is some sudden resistance to the flow. So that uh, leads to sudden hike in pressure. So that is also taken into account by considering a higher factor of safety, 9. So into 2T is 2.5 divided by 1000 because it's in mm divided by diameter. Outer diameter is considered here. And this was not required anyway. So 320 into 10 power 5 multiplied by 2.5 divided by 9. So I am getting around this is what I am getting. Just cross check once. Okay, so I'm getting 8.8 into 10 to the power 6 Pascal. So this is the answer. I think in the assignment, C was given as the correct option. I am not sure to check it up, but I think the numerical is correct here. I mean, the answer should be 8.8 into 10 to the power 6. In case of any mistake, just let me know. It's close to this one only. So generally, if you are seeing that in option, you are seeing values that are higher than this. Like you should be always choosing the lower possible value because the question asks safe working pressure. So had there been like if an option was given as say 9 or 9.5 into 10 to the power 6 Pascal, that is not a safe working pressure under this conditions and factor of safety. But 8 is a safe working pressure. So this is the correct one. Next, I mistakenly repeated it. Storing the hydraulic fluid and separating the contaminants. The rule of thumb allows the hydraulic fluid to dwell in the reservoir for at least how many minutes before being pumped into the hydraulic system. So it is important for the hydraulic fluid to stay in the reservoir for some amount of time so that it is able to dissipate the heat and also at the same time uh, it gets filtered out of the contaminants. The contaminants should be allowed to settle down as the fluid is flowing through the baffle place. That's why you provide some resistance to the flow in the reservoir by providing baffle plate so that the contaminants get separated out. So obviously it slows down the flow of fluid and you need this time of dwell, and accordingly you should be designing the hydraulic reservoir. So 10 minutes, 30 minutes, 30 seconds, 3 minutes. So it should be close to 3 minutes. The following are the biodegradable hydraulic fluids. So as we know that nowadays the ecological factors are pretty much taken seriously by different plants and constituting committees. So there is a shift. You can say it's a paradigm shift from the usage of synthetic chemicals or chemical based hydraulic fluids to biodegradable or bio based hydraulic fluids because they don't cause any harm to the environment or to the health of the uh, operators. So rapeseed oil is one of them. Phosphate is a chemical. It is not a biodegradable fluid. Next, you have HETGS. So HE means what is the meaning of HE? HE is basically your hydraulically environmental fluid. So hydraulic environmental. So basically, HE stands for hydraulic environmental fluids. So HETG means this triglyceride based oils. It is derived from plants. Then HEPG means polyglycol based oils. You have others, synthetic ester based HEES. Then uh, yeah, so these are biodegradable ones. What about water glycol? It is not biodegradable. Phosphate ester is also not biodegradable. what are the roles of additives? So, just I wanted to discuss a few more things before concluding today's session. Uh, some theoretical aspects which may come as a question, or it can be asked, you know, as a case study also. Like not a case study, rather you can be asked to select particular uh, some of these auxiliary systems, like what type of hydraulic fluids, what type of hydraulic conduits for designing a particular hydraulic system. So it can be asked as a like a larger question, as a design question. So that's why this thing should be thoroughly, kept in mind. Like while you are selecting any particular hydraulic fluids. So hydraulic fluids can be of different types. It can be water-based fluids, or it can be oil-based fluids. Like it can be some synthetic hydraulic fluids. It can be some biodegradable hydraulic fluids. So if not all the fluids are applicable under all uh, conditions of pressure, temperature, and other environmental factors, so they need to be chosen very judiciously before being used. Suppose the oil that is being used in some application in India may not be applicable to some European countries where temperatures may fall below the freezing point. So there you need to be using some oil that can retain its viscosity without getting frozen. So particularly in mobile hydraulic systems like cranes and all. So so these are some particular things that should be kept in mind. The question asks the role of additives and inhibitors in hydraulic fluids. So as the name suggests, additives are added to the fluids to enhance its property. What are the properties that are generally desired out of a hydraulic fluids? Its flowability, its lubrication capability, which is also known as lubricity. Then uh, its ability to uh, reduce the wear of components. Then de-emulsibility. So these things should be uh, kept in mind, and also it shouldn't be foaming. So anti-foam properties should be kept in mind. So I'm just writing down what is the role. So additives, just it can be used to increase the lubricity, reduce wear of components. Then anti-foaming properties, because if it forms a foam and the hydraulic reservoir, the heat to dissipate out, and that will be again a secondary problem, because the viscosity and other physical properties may change with increase in temperature. So anti-foaming properties, then demulsibility. So accordingly, you have different types of additives like anti-wear, uh, anti-foaming agents, demulsifier, then extreme pressure additives, all these things. What about inhibitors? So by the name, it means that it inhibits certain negative things associated with the particular hydraulic fluid. So first of all, hydraulic fluids, if it is containing water, it will inevitably lead to corrosion of iron-based, steel-based components, and also it can lead to, like for other fluids also, the oxidation of the particular components is one of the major challenges. So inhibitors, its role is prevent chemical reaction, because this is completely undesirable. You only want uh, the fluid as a you only want the fluid to be carrying your energy, right? You don't want it to react with your system. So this under this the anti-corrosion and anti-oxidation properties come into picture. Then yeah, this is the main thing, main role of the inhibitor, which should be taken into account, and these are added as supplementary things to your hydraulic fluid. These are additives basically. Okay. Next, as I already said, that while selecting a hydraulic fluid, many things should be kept in mind. So, what are those things? What are the factors that should be kept in mind while selecting a hydraulic fluid for a particular hydraulic system? Number one is your operating pressure. Based on your load, how much load is required, you need to calculate the energy, and accordingly, the fluid energy is just basically delta P into flow rate, that is Q. So, first, your delta P needs to be uh, like based on the particular application, your delta P is fixed. So that is your operating pressure. Right. Flow rate is again like it is modulated by the pump based on the requirements, based on the speed of operation. So that is like another thing. That, but that is not a determining factor for a for selecting a hydraulic fluid. But yeah, but the related factors are there. I'm explaining that. So first is your operating pressure. Next is your temperature, operating temperature. So if your temperature is high temperature applications, then you should be using some type of fluids. If your temperature is drastically low, like I said, in polar regions or in countries where or in places where temperatures go below the mm, freezing point, sub-zero temperature. So there it becomes a challenge because while starting, the hydraulic fluid gets frozen and it becomes difficult to start the machine. So you need to heat up the system to allow the uh, fluid, to allow the hydraulic fluid to start flowing. Defreezer is required in such cases. Next, lubricity. This is the ability to, like, this is the flowability, I would say. Not directly flowability, rather its ability to lubricate the parts. Sorry, it is not flowability, rather its ability to lubricate the moving parts. Particularly while you have sliding contacts, like in piston cylinder arrangements, or your motor placed in bearing. So these are the things. Then, as I said, like what determines the Q, that is the flow rate. Like what what are the considering factors um, for that? So that is the speed of operation. So operating speed, I would say. Based on this, also you have to select. Um, Next is your contamination levels, like where you are using it. Then other factors are there like safety, then expected service life. I'm just including safety here only. Another important thing that I missed out is environmental condition. First of all, in what condition you're using it, whether you will be using any chemical based hydraulic fluid or a biodegradable hydraulic fluid. Next is your cost. So this I am writing in capital because this is the main thing that comes into picture. So the cost of transmission. So these are the factors that affect the selection of hydraulic fluid. Factors affecting the selection of hydraulic conduits in a hydraulic system. Again, like while you're designing a particular hydraulic circuit for any application, uh, you need to select what material or what should be the length or the geometrical features for the hydraulic conduit system. So one thumb rule is generally like not thumb rule, rather uh, as the designer, you should try to minimize the material usage while providing the optimal, you know, while maintaining the optimal performance, right? So as I say that you will be minimizing the material usage, it also should be taken care that it's within the safe limits. Like the safety should be of prime importance. So here also, like while you are looking into hydraulic conduits, there are different materials that are being used, like plastic, stainless steel tubes. Like stainless steel can be used. Then you have rubber also, based on different applications and different pressure. So here, so first and foremost thing is your pressure, operating pressure. So again, pressure can be of like while you're taking the pressure into consideration, you shouldn't only consider the steady state pressure, which is the generally what we are seeing in the numericals. Those were the steady state pressures. But at the same time, you should also consider the pressure hikes. Suddenly, there is some. So suppose this there is some spike in pressure. This happens when, as I already discussed, when there is some sudden resistance to flow of fluid, like when a valve is closing or you're changing the direction in the direction control valve by moving the spool. So temporarily there is a blockage in the flow of the pressurized fluid, and it's flowing at a substantial velocity, say around some 5 or 6 meters per second. So as you're stopping it, there will be sudden conversion of this kinetic energy into pressure energy. So that increase in pressure will send out shock waves in will dissipate the energy in the form of shock waves. So that can damage your hydraulic conduits if you are not taking care of them. So this both of these things should be taken into care by allowing a substantial factor of safety. We already discussed this in one of the numericals. Next is your flow rate or discharge. How much fluid flow are you accounting for a particular application? That is Q. Next, what are the environmental conditions? Environmental factors, I would say. So under this, many things come into picture, like the temperature, the type of fluid you're using. So I'm writing here the fluid that you're using. This is in direct contact with your hydraulic conduits. So obviously, uh, there are chances of corrosion, oxidation. So accordingly, you should be choosing the particular type of hydraulic conduits. Next is the temperature. How much temperature is it operating? Whether it is high. If it's high, then plastic is not recommended. Rubber is not recommended. Then you have to use stainless steel. In corrosive environments, you have to use stainless steel. But again, if you use stainless steel in all places, then it is incurring huge cost. So that is again not desirable. So these things should be optimized. Next, As I said, it's okay. So vibration, it's another important thing. So as you know that when there is vibration, there are chances of uh, losing of components. Like the components become loose when you have some threaded parts. So there are chances that they become loose. So accordingly, you should be choosing the fittings so that they don't become loose during the operation. Otherwise, there will be possible chances of leakage. Next, one important thing is flexibility. Whether you need a flexible hose. So where do you need flexible hose? Where you have moving elements. Suppose the two parts between which the fluid flow is happening, there is a relative motion between the two parts which is connected by a hose. So there you need a flexible tubing, or there is a relative movement of uh, uh, points where the conduit is being fixed. So there also you need a flexible hose. So the relative motion is a fact. Just a common example. Suppose you have a table here, and on this table you have a hydraulic motor. Okay. So this table is not stationary. It is moving in x y direction. Say so. It is moving in x y directions. So the motor, it is being supplied with hydraulic fluid. So there will be two hoses. One is the inlet, one is the outlet. So as this is, and accordingly this is rotating. So as this motor is also moving along with this table, so this hose will also be moving. So this should be flexible. Okay, because you don't want the valves also to be moving along with the motor. They are fixed at a particular place. You don't want the stresses to develop in this particular hoses as it is trying to move around. This is very common in drilling machines, milling machines, where you are using hydraulic motors. Okay, next is your foremost thing, that is safety and also cost. So yeah, that's it. So that is all for today's session. I hope I have understood the problems and also the other theoretical portions that we tried to cover here. If you're having any other doubts, you can always post in the NPTEL portal, and we will meet again for the next session the next week. Thank you